Should I start now? So, hi everyone. Let me check first. Okay. So, hi everyone. I am Anuj Kumar. I'm working as a Prime Minister Research Fellow at IIT Roorkee, and this is the assignment 3 of this course, which is entitled as Trace and Ultra Trace Analysis of Metals using AAS, that is Atomic Absorption Spectrometry. Okay, so I am the TA of this particular course, which is instructed by Professor J.R. Mudkavi, IC Bangalore. Okay, so this is the first question of this assignment 3. So, what will be the pattern of this interactive session? I will first display a question and I will wait for 2 to 3 minutes for the response, and after that, I will explain it. Okay, so this is the first question that is related to Fraunhofer lines. So here is asked, that is what do Fraunhofer lines indicate basically. So here are four options provided to you. They can indicate there are many elements in the universe. Second one, there are many elements in the moon. There are many elements in the lunar spectrum. And the last one is there are many elements common on Earth's and solar atmosphere. Okay, so I'll wait for 2 minutes for your response. If no response is there, I will explain. You can type in the chat box also. Okay, so the correct option for this option, for this question is, and this one, there are many elements common on the Earth and solar atmosphere. So this particular option can be explained here. You can see the pattern for Fraunhofer lines. Okay, if there is a source of continuous spectrum like the solar system, and this is emitting radiation, that is before interaction with cloud of gases, it is like a continuous spectrum, and after interaction with cloud of gas, some specific wavelength are absorbed by these gaseous clouds. Okay, so they can be seen as a missing lines in this spectrum. Okay, so, and this another one, these are the missing line you can see here, that is emitted in any other direction. Okay, so same phenomena can be observed in the on the earth also, because there are also a cloud of gas. So basically this is the origin of atomic absorption spectrometry. So this last option is the correct option. Okay, so the next question is a numerical type question. You have to basically calculate the energy difference between the first resonance line and ground state of an element. Is uh, this is the energy value difference is given to you, that is 2.102 electron volt. Okay, if the transition is accompanied by emission, what would be the wavelength of emission? Okay, just try to calculate. I'll wait for 5 minutes, because this is a numerical type question, and I After that, I will solve it. Are you trying to solve? No response. Okay, what will you do? The expression for energy difference is this one. Okay, so delta is given to you 2.102 electron volt, right? And Hc upon lambda. Okay, you have to basically calculate this lambda value. Okay, so lambda equal to Hc upon 2.102 electron volt, or you can write it 2.102 into 1.6 10 raised to minus 19 joules, right? If you put the value of Planck constant here, that is joule second, and velocity is 3 into 10 raised to 8 meter per second, right? And this one will be like this. Okay, so the 6.6 into 3, it will be 10 raised to minus 26, and divide by, and a plus 19 added here. Okay, this second will be cancel out, joule will be cancel out. Okay, you will be getting the value of delta in meter. Okay, let me solve. 6.6 divided by 2.102, that is 5.88 into 10 raised to minus 7 meter. If I convert into micrometer, that will be 0.588 micrometer, something like that. Okay, so the first option will be correct. Okay, is it okay? Easy formula you have to apply, and after putting the value of this H and C and a minor unit conversion, you will getting this one. Okay, if it is okay, just type okay in the chat box so that I can proceed with the next one. Okay, right. Thanks. Okay, so the next one is for Einstein emission and absorption coefficients. This one is extra. Yeah. For Einstein emission and absorption coefficient are non-zero. Okay, absorption coefficients are non-zero only if the energy levels are of opposite parity and delta J barabar can be any number greater than 2. They can be of same parity and delta J equal to plus minus 1. That can be opposite parity, and the fourth one is the same parity and delta J equal to uh, any number greater than 2. So any idea? Okay, so the the before discussing these parity and all these rules, you have to know about the Einstein emission and absorption coefficients. Okay, so in the theoretical classes you have already read this expression. Okay, so this is the here this a term is called as Einstein emission coefficient for this particular transitions, right? Basically, this expression tells about the transitional probability, right? So higher the probability of transitions, greater will be the intensity of emission. Okay, so this is the value of this a value. This lie in this range, right? And similarly, if I talk about the absorption, absorption coefficient, this one is 2 1. B21 is the Einstein absorption coefficient. Okay, it basically if n2 atoms are there in lower transition state and they get a radiation of frequency nu. Okay, basically the new frequency is derived from this equation, and basically you have to include the volume flux density here. So the number of n2 21 atoms that will absorb at radiation is obeyed will be obeying this expression, right? So this is your theoretical part. The emission line of any transitions is approximately 10 to 10 raised to minus 8 second, right? So if there are sufficient number of atoms, okay, so steady state emission or absorption phenomena can be observed. For atomic absorption to occur, intense emission of the desired element must be generated first, right? What it is describing. Like say if this is the ground state and this is the excited state. Okay, so there should be a higher pollution populations of the atoms should be in their ground state, so that if I irradiate with any radiation, so the sufficient number of atoms can get transit to the higher energy level state. Okay, so the general selection rule for this allowed transition is they should follow this rule, that is delta J is equal to plus minus 1, or the levels involved are should be of opposite parity, right? So if I am writing here two symbols, that is this transition, this is the J value. If I calculate delta J, it will be 1. So this transition can be easily happen. Okay, so this third one is the right option. Basically this question is directly from theory. So next one is related to the Doppler effect. So the Doppler effect in the spectroscopy results in the first is the shortening profile of the resonance line, second is the broadening profile, third is the shifting of the resonance lines to longer wavelength, and fourth one is the shifting of the resonance line to shorter wavelength. In lectures, you have already read about the Doppler broadening effect. So you can directly mark from here also. So Doppler effect in the spectroscopy generally tells about the broadening profile. Okay, so what effect this causes the broadening? If I talk about specifically about this Doppler broadening, so in the sound you have already read about the Doppler effect. Okay, so let's say if there is a photon detector here and x number of photons are coming towards this photon detector. Okay, so wavelength will be increased, right? And if there is a decrease in and there if the photon are going away from the detector, then there will be a decrease in wavelength. So that causes the broadening in the peak, right? So if this is the half of the intensity, and if I place two perpendiculars here, so this delta lambda will be called the Doppler broadening. Okay, simply if we talk about the bandwidth in any spectrometer, if we are saying that we are working on 365 nanometer with a width of 5 nanometer. Okay, so what the spectrometer is doing actually, so it is providing the radiation ranging from 360 nanometer to 370 nanometer, right? So delta lambda will be 5. Okay, so here is the same case. If this is the delta node, right? This is the desired wavelength. Okay, but if there is a bandwidth of 5, so altogether you are getting the these other wavelength transitions also. So here it is also written the same here. If an atom emitting a radiation delta node, moves with a velocity v relative to the observer wavelength is given by this expression. So there is an increment. Delta is equal to delta naught plus delta naught v1. This expression is basically derived from the Doppler effect. Okay, and the next is related to the Lorentz broadening of the spectral lines. So four options are there. First is pressure broadening, including these all effects, Stark, Boltzmann and Van der Waals effect. Second is Stark effect only. Third is Boltzmann effect only, and fourth one is the Van der Waals effect only. Okay, these are the direct questions from the lectures. So Lorentz broadening is basically the collective name of these all effects: Stark effects, Holtzmark effect, and Van der Waals effect. Okay, and we can say it also the pressure broadening, right? So I'll explain in the next slide. So this is the pressure broadening. Okay, so for atomic absorption spectrometry, we need the atoms in the vapor state. Okay, so there is a perpetual state of motion. Okay, and the collision of atoms is inevitable, causing radiation quantum lighting different frequency to be absorbed or emitted, right? If there are several atoms and they are colliding with each other. Okay, so if there are, so the interacting particles, if the interacting particles are charged, okay, plus minus or something like that. So this if the broadening is due to the charged particles, this is called the Stark effect. Okay, because if we are generating the vapor of any atom, like if we have used the atomization procedure, so every time you are not getting the atoms in the ions form, or you will not be getting the atoms in the neutralized form. Okay, so there will be some uncharged particles also there. Okay, so if the broadening is due to these uncharged particles, that is called the Van der Waals effects, because the Van der Waal effect predominate in that case. Okay, so another one is the Holtzmark effect, that is collision between atom of the same type, leading to this resonant broadening. Okay, that is called the Holtzmark effect. So basically, it is very complex to identify that which effect is causing the broadening. So altogether, we can say that this is called as the Lorentz broadening, and these all effects are categorized under this broadening. So here is the peak profile. You can say in the case of Doppler and Lorentz, in the Doppler broadening, what you can observe. So the delta lambda is less, right? And in case of Lorentz, it is a very high delta. So the at high pressure, so Lorentz broadening uh, can predominate, which is arise by the basically the collisions between the atoms. They can be ions, they can be atoms, neutralized atoms, right? The next question is in the expression. This is expression, right? Which this xv terms you have to define what it is. Okay, so this is the transmitted intensity, or you can say flux, and this is the incident. Basically, this is a form of Beer-Lambert law. This is a easy question. So you can type the answer in the chat box. Spectral emission coefficient. Okay. So how you can say this is the spectral emission coefficient? Any idea? Because Beer-Lambert law generally applied for the absorbance or absorption. So this is the theoretical background for this formula. Okay, so this is the radiant flux, that is phi. It may be proved that absorption factor, or you can say the optical density, is proportional to the concentration of free atoms and the path lengths in the absorbing medium. Right. So this is nothing the Beer-Lambert law, which can be expressed as this expression. Right. So this is the path length L, and N is the number of atoms, right? And this is the rate flux, transmitted flux and incident flux, and XV is the spectral absorption coefficient, right? Basically, we are discussing about the atomic absorption spectrometry, okay, and also the Beer-Lambert law is applicable for absorption, okay. So from that you can get the elementary idea, that is XV is the spectral absorption coefficient, okay. So I'm going to the next one. Yes. So if an element has a resonance line below 200 nanometer, double S determination is difficult. Why? It is difficult below 200 nanometer. What are the interfering particles or interfering atoms? Right. You have to basically identify among these four options. There can be nitrogen and oxygen. There can be nitrogen. There can be oxygen only, and none of these. Okay. So. Uh, Less than 200 nanometer, we generally say it is a vacuum UV, right? So, since all the elements can be excited to next high energy level, okay, in theory, any element can be determined by atomic absorption spectrometry by this simple idea, okay, not always. So, below 200 nanometer, analysis of this arsenic, selenium, iodine, sulfur, etc., etc., it is difficult because of the incipient absorption by oxygen, right? So, what that mean? That means in the vapor phase, we would come across not only the free atoms but also some water molecules, oxygen molecules, nitrogen, and several other species also. Okay, so if you want to determine any element, you have to first get in the vapor state. Okay, if the absorbance line is less than 200 nanometer, then oxygen will also absorb, right? So you if any absorption band, if I talk about the absorption band here, so this is not the pure band of the element only, right? Oxygen can also absorb, or oxygen can also interfere with this band, because it can also absorb the radiation below 200 nanometer. So the actual intensity of radiation would be the sum of atomic absorption as well as molecular absorption by species like oxygen, nitrogen, nitric acid, etc. Even though arsenic, selenium, these one have also resonance lines with below 200. So the absorption by oxygen and hot flames gases prevent us to get very clear picture, right? So it can be absorption by both oxygen and nitrogen. Is it clear? So this is the interfering nature of these molecules. Okay. So the next one is the Russell-Sanders coupling, refers to the resultant vector sum of the momentum orbs. Okay, that is R. So R can be or J can be J. That is coupling constant can be L plus minus S. Right. So this is the angular momentum, and this is orbital angular momentum. This is the spin angular momentum. So both contribute to this coupling, right? So third one will be the right option. Next question is find the term symbol for this P2 configuration. Okay, just fill the electrons. Okay, plus one, zero, and minus one. Right. So there can be many configurations of filling these electrons. Right. You can fill it something like this. You can fill it like this. You can fill it like this, and you can fill it like this also. Okay, and same for the opposite configuration. Okay, there can be many cases you can try out by filling these electrons, and in how many ways you can fill the electrons. So I am taking this one, that is a simple one. Okay, these are the angular momentum quantum number. Okay, so if you have to find the term symbol, that is 2s plus 1 lj, right? So if this electron, let's say first calculate the total multiplicity. Okay, uh, its spin is plus half, its spin is also plus half, so you can calculate the total spin is 1. And if I put the value of this s here, so you can get the value of this whole term, that is called the multiplicity. Okay, so it will be 3, right? 2s plus 1 will be 3. Okay, if I'm talk about if I talk about the value of L, okay, so just multiply by number of electrons by this value. Okay, that will be plus 1 into 1 plus 0, that will be plus 1. Okay, so what you can get from here, if I write 0, 1, 2, 3, that will correspond to S, P, D, and F. Okay, so L will be P, right? So the term symbol will be 3P. Okay, and if I calculate this coupling constant, that is J is L plus S. Okay, that will be 1 plus 1, that is 2. Okay, so simply you can put the value here, right? There are many other cases also. I'm not going to the deep discussion of this term symbol. Okay, there are many other conditions also. If you are having any more than half filled orbital, then rules are different. Okay, I'll explain in other some other lecture. In the last lecture, I'll explain the total rules for calculating these term symbols. Right. So is it understood? Okay. So you can similarly you can calculate uh, the term symbol for all the configurations. Okay. So these those term symbol will be all the possible term symbols for this configuration, particular configuration, right? So the next question is, the free atoms exhibit only vibrational transitions, only rotational, only electronic transitions, or all of these. In atomic absorption spectrometry, we are only dealing with free atoms, right? For that purpose, we are using the atomization procedure. Okay, so free atoms exhibit a particular property that uh, they can exhibit only electronic transitions. They, they do not exhibit the vibrational and rotational transitions, right? If you are having some molecule, right? This is the carbonyl compound. Okay, so this will also be having some rotational transitions also, and some vibrational transitions due to this functional groups. Okay, this bond will vibrate when any radiation is passed through. Okay, that is basically you read in the UV spectrometry. Okay, but here what you are doing, you are just vaporizing the atoms and you are getting the atoms in free state. So the electronic transitions only take place. So this third option will be the right option for this question. In the last question, that is the in the spectrum of an element, absorption lines are more than emission lines. Emission lines are more than absorption lines, or they are almost equal, or it cannot be predicted. The last question, and I'm just waiting for one answer. I'm giving you a hint. If it is n equal to 1, equal to n equal to 3, and if I am providing the energy that is sufficient to for the transition from 1 to 3. Okay, So you will be getting a few absorption lines, right? And if I talk about the emission lines, can you predict the emission lines will be more or less than the absorption lines? So emission lines are almost more than absorption line. Why? Because this atom can also fall down to this level and emit the radiation, and this can also fall down to this ground state and also emit the another radiation. So you can basically get two emission lines, right? So the second options will be the right answer. So that's all for today. If you are having any query, you can just ask me. Okay, thank you for attending. If there is no question, you may leave, please. And thanks for attending again.